This conference will now be recorded.
So now let's start again with the dropout. So if you remember, especially those of you who attended the first part of the training, we did what we call bagging. Do you remember random forests?
Yes.
You remember random forests? What we did with random forests is to use multiple trees to improve the accuracy on testing. We saw that decision trees, even if you haven't attended that part, guys, it's a good, also it's a simple thing. So we have a data set and we divide it into two parts, training and testing. And this is for training. So we saw that the decision trees, if they are too big, if they have a big length, what happened? What happened with them? What was the main problem with decision trees, guys? What was the main problem with decision trees? They tended to overfit.
Overfit.
Yeah, exactly. They tended to overfit. They had high accuracy generally if the tree is big. They had the high accuracy on training tests, on training set, sorry, and the lower accuracy on testing. So one of the techniques that we used to improve them is called what? Random forest, which was basically building many trees highly uncorrelated by making them different with some tricks that we saw. So the more we build, the closer the accuracy on training and testing became. It's like, and they were just voting. So we built a lot of trees that are different by doing some tricks during the construction. And after building them, when they vote, the accuracy on training dropped a little bit, just a little bit, but on testing was very close. It improved here a lot. So their power in generalizing became higher, and we call that bagging. We had something similar with neural networks. And ensembling, generally, like I said, ensembling methods always like to win, most of the time they win machine learning competitions. However, in normal situations, like for random forest, we needed to train multiple trees. And in deep learning, training multiple models, it costs a lot of time. It's a lot, it's a very heavy process. So what we do, there is a very clever trick. It looks very simple, but so powerful. We have a neural network here. And what is dropout? We randomly deactivate at each iteration. So when we use the gradient descent, we said the stochastic gradient descent. What we do, we have the data set, and we sample a little bit of the data set. We do one phase, like one epoch of training, where we modify the weights, and then on the next epoch, we do the same thing. We resample randomly, for example here, or from the data set, and we do the same thing again. So the dropout for each epoch, each iteration, what we do, we remove some neurons randomly with a probability. We set a probability. So we remove some. So at each iteration, guys, what is happening? At each iteration, we are having a different network. Do you agree with me? Like sometimes we remove this, and this. Sometimes, so at each iteration, we are having a different neural network, slightly a little bit different, depending on what we removed. Okay, guys? And because we are doing that, what is happening? it's like some form of bagging. Each iteration, we are having a different neural network, but the neurons don't change. The neurons don't change. It's similar to bagging, but bagging use voting. At the end, we have multiple models, and there is voting. They vote. But here, neurons are averaged. So what we have, the weights in each neuron are averaged in each iteration. So they share the same weight. And at the end, the effect will be like we trained different neural networks and averaged all the weights. By doing that, the accuracy and the model will be regularized, and it will be less likely for the model to overfit. And we always will receive a higher accuracy on testing. Can you see that what is happening, guys? Can you see this effect of dropout? Tell me, please, guys. Not clear?
Reda, it seems like you are reducing the neural network, and after it seems like it will be like faster. Is it correct?
For each iteration, it will be faster, but in total, it won't be faster.
In total, it will be like the same.
No, it will be slow. It will be slower. In total, it will be slower for each iteration. Because we are learning iteratively in a neural network, so we do a lot of epochs. So for each iteration, we are removing some. So of course, it will be faster, but of course, it will not converge quickly because each neuron, each neural network that we are producing is going to go into a certain direction, into a different direction. So it will take some time for them to converge to the same direction. It will be, in total, it will be slower. Generally, it was the time or something like that. But the accuracy will be a lot better.
But in this case, we will not lose some kind of information because we are removing some learning. We are removing some nodes.
We are not throwing them out. We are deactivating them. On the next iteration, we reactivate everything and we deactivate others. We are not losing. We are not throwing them. At the end, we keep everything. We don't remove any of the nodes. We keep them, like in here. But they will be trained differently. So each neuron is trained by different iterations. So for example, if let's say this neuron was trained to recognize a nose. In the next iteration, it will be removed. And we see if we can recognize this face without the nose. If the nose is important, it will be duplicated. Another neuron will try to learn the nose, because without it, we can't recognize the face. If it is not important, we will find something else that will recognize the face. For example, the eye or something else. So it's like the effect, it will diversify what we will learn here. We will have a lot of diverse features. It's like a bit hard to explain that way. We need some experience, so to practice a little bit to understand it. But what is happening is in each iteration, we are training a different neural network. And
in
then
fact, it's
we are, and then we are averaging them.
Yeah, sorry.
Go ahead.
In fact, it's like you want to say it's like we are avoiding the duplication of the learning, something like this.
Not really. Not really. It's a little bit complex if we take it from that point of view. But what is bagging? Bagging is we train multiple models, M1, Mn. Say 1,000 models. M2 here. And these models are a little bit different. all of them are different. Like in the random forest, all of them, the trees are slightly different, or more than that. In the neural network, we can do the same thing. We can train them. We can build different neurons, one smaller, like this one a little bit smaller, taking only this. And when we have multiple models, M1, M2, MN, or M1000, we can do that. And then what will happen, we will average them. This is the normal bagging. Are you happy, Farouk, with this explanation first? Do you understand what I mean? This is the normal bagging. So we can, exactly, we can have multiple models, and then we make them vote. However, training 1,000 neural networks will cost us a lot of time. A neural network is much more difficult to train than a decision tree. Decision tree is very fast, but a neural network is a lot more complex. So we don't want to train multiple neural networks and then make them vote. Instead, we use this little trick called dropout. What is this dropout? For each neuron, we deactivate it. We deactivate one neuron or some neurons. So in each iteration, we are using a different architecture. But the nodes, they don't change. When we use another architecture, we keep the same nodes and the same weights. So what is happening is like an implicit bagging. We are averaging all these models, but indirectly, by making them like each iteration, we make the neural network go into a certain direction, train differently. But like it's like we are training all of these models by one single architecture. It's like one single architecture is carrying the power for all of these models. And it is like really like building these models implicitly, not explicitly. Here it's explicitly in random forests or this method, but here it's implicitly. And we are averaging things not by voting, but at the neuron level. At the end, of course, we keep everything. We reactivate them, and we keep this connected to all of them. We revert back to this architecture. And by doing that, it's incredible, but it works a lot better than using one single neuron like this without dropout. And we are going to see an example, the first example that introduced a dropout and how much it improved things. Are you happy with this explanation? Silence?
Yeah, thank you.
No, I need some more clarification. I missed it.
That's fine. Let's repeat it again. We don't understand it quickly the first time, guys. Don't worry about this. It's like something I've seen a lot. So we don't understand it like that quickly the first time. And by the way, guys, it's totally fine if you don't understand everything. I don't understand everything till now, like in the whole field of machine learning. I still like struggle with certain aspects. So that is completely fine that you need to repeat things and read about things multiple times. This is how this area is. So are you happy, Yusuf, with bagging is multiple models being averaged? Are you happy with this?
Yes, okay, yeah.
Yeah, like in the random forest, we built multiple trees and correlated different in their how we built them, and then they vote. And we said that this method improved accuracy on testing and reduced overfitting. We said that this, and it happens a lot. Like this method, that what we said, the random forests are a lot more powerful than decision trees. It's actually one of the really good models, one of the best. But we can't afford that with neural networks. Why, Yusuf, we can't afford it? Why we can't afford building multiple neural networks and doing the same strategy like with random forests? And building something like random neural network. It is possible and it should work, but
overfitting.
no, it's not overfitting. Well, we do it for overfitting, to reduce overfitting. If we build multiple neural networks like this one, slightly different, and we make them vote, like for the random forest, we should improve the results. It will be like applying bagging to neural networks. We should improve the results. Do you agree with me?
Yes.
Yusuf, do you agree with me? Where did you disappear? So bagging is this principle. We use multiple models and we make them vote. These models are different. They are not the same, exactly the same. It could be multiple random decision trees, but they are different in their structure, not the same. And it should improve the results. This is like observed most of the time. We can do the same thing with neural networks. We can build multiple models, M1, M1000, so 1000 neural networks. And we should improve the results. It should improve them. Are you happy with this, guys, so far? If they vote, we get better results. This is the principle of bagging.
Yes. Yeah.
But what's the problem with this, with training 1000 neural networks?
Is it slow?
Is it long?
Super
expensive?
slow. Super slow, yeah. Super slow. Sometimes I remember I trained a few months ago a neural network on a machine that costs around $100K on dollar. It means it's a super powerful machine. It took me around 12 hours because the dataset was big and the network was relatively big. The machine costs around $100,000. So it means it is super powerful machine. And it took me like 12 hours. And I stopped it. I didn't complete the training. I could train even more. Some models take like 5 days easily for one single neural network. So imagine if we train this kind of models 1000 times. It's not practical. So if it is half a day, 1000 times, it's just like 500 days. 500 days, it's just over a year to train a model in this kind of machines, guys. It's over a year to train the model to, if you can get hold of this machine, $100K machine. So what shall we do? The dropout is a powerful method to do the same thing. It's like we train multiple models, but implicitly, not explicitly like in here. Implicitly, what we do, we remove neurons at each iteration. We remove them randomly. So in iteration 1, we can end up with this architecture. Iteration number 2, we can end up with other architecture, completely different. Maybe we have just 2 neurons here, all of the neurons here, and well, these are the input. Well, if they are the inputs, we can still have this. So in each iteration, we are using a little bit of a different neural network. And if we keep doing that, it's almost like we are having an infinity of architectures, almost. Yes or no, guys?
But, sorry, I came late, Reda.
Okay.
Like we are the one who choose how many iteration, because depending.
Yes, we choose generally a number of iterations.
Okay, so that means if we are the one who choose the number of iteration, let's say that we choose only 2, is not enough randomly.
No, 2 is very low. No, 2 is super low.
Okay.
We generally go a lot higher.
It's like how many? How much is the minimum?
It depends on the problem.
Okay.
So generally, if we are talking about CNNs, about what we are going to talk to today, if we have time, Generally, like 20 is okay. 50 is better, but it really depends on the problem.
Okay.
And the kind of, if you are using transfer learning, you're not using with transfer learning, for example, you will need less. For example, 10 will be fine.
Okay. So
For example,
it does mean 50 cover all the possible random network neural.
It doesn't look at all the possible configurations.
Okay.
It does it randomly.
Okay.
It does it randomly. So we end up like, if we have 50 iteration, it's almost like we are using 50 different architectures.
I see.
And at each iteration, each one of them is trying to, of course, solve the problem. And it is like what we call a NIM. I call it that way. I prefer to call it an implicit bagging. It's like bagging, but we don't really produce 1,000 models. We just make the model look like we have more models in one. So it's a lot faster than doing this, but it does almost the same effect. Almost we have the same effect as here, as in here. And in practice, it improves things a lot. I can't imagine training a neural network without dropout, guys. So far, I have never used like training like neural networks without dropout in some part of the network. Are you happy, guys, with this explanation? It's not easy like to understand exactly deeply what is happening, but we can see that in each iteration we are having a different network, and all of them are trying like to do the same thing, like to produce good results, good accuracy. So they will get, and neurons are like averaged across networks, the different neural networks. Neurons are the ones that are averaged, not like the voting. We get some kind of voting or averaging inside the neurons. Instead of bagging, we get it at the output in bagging. But here, we get it at the neurons level. And this will improve things a lot. So guys, really, this is understood intuitively, not like you are not going to understand it purely by logic. You understand it intuitively, that you can just feel how it's going to work. Shall we move on, guys? Is it fine? Tell me, please.
Yes,
Yeah.
totally.
It should be all right. It should be. You're not going to understand it today 100%, but you get a feeling of what it does. If you get the feel, that's fine. So this is the dropout. Here is an example. So we have these architectures have 2 to 4 hidden layers. So we have multiple architectures depending on the color. So we are training multiple neural networks. So here it's without the dropout. This is the error, classification error. We train the neural network without the dropout. This is untested, by the way, when we tested things. So without the dropout, we got this kind of error, about between 2% and 1.5%. These are small neural networks, 2 to 4 hidden layers. And this is the number of hidden units. So we can see here. And when we add the dropout, look at what happened. The error almost dropped almost to 1%. It was still good, okay, without the dropout here in these cases, but here it really jumped. You can see this, the effect of the dropout. And these are the number of iterations, number of, if we can call it that way, the number of weight updates. So here we have 100, I think it's on the total number of weights. So you can see the effect in how many examples do we have? 1, 2, 3, 4, 5, 6, like 7 cases here. We have 7 cases. All of them improves with the dropout. 7 different neural networks with different data sets, and all of them, not a single one, is worse with dropout. It's always better. Can you see that, guys?
Yes, yeah.
So it's always good to have a dropout. So now And it is probably the most used regularization technique in neural networks. Probably the one that is used the most. Now let's look at some gradient descent variants. And we are going to conclude this chapter. I'm sure you will be happy to conclude it. So let's look at some SGD algorithms, stochastic gradient descent. Can you guys remember me? What is the difference between the regular gradient descent and the stochastic gradient descent? What's the difference between the regular one and the stochastic one?
I think the stochastic, it's in batches. So you do it in batches, and the regular one, you just do it all the data in all together.
Perfect. Thank you, Cecily. Yeah, that is the difference, the main difference. And the batches are, how are they produced? Like we divide the data set, we choose them randomly. How do we do that? Do we like, so if we have here the data set, we divide it into batches like that, or we just produce batches randomly. So each batch is a random combination of some rows. How do we do it? So there is the batch gradient descent. The batch gradient descent is just we divide the data set into batches. But this one is not used a lot. We use the stochastic. When you hear the word stochastic, it means we choose them randomly. Stochastic means there is probability. We choose them randomly. The batches are sampled randomly from the data set. If, for example, we have 1,000 rows and we want a batch of 100, we just take 100 randomly and we put them here, and we build our batch. Okay, guys, this is the stochastic gradient descent. Happy so far?
Yes.
Perfect. So there is a big problem. I'm sure all of you understand what is the gradient descent so far. Otherwise, I will be depressed. All of you are happy with what is the gradient descent, I hope.
Yeah.
Perfect. Now, guys, I won't be depressed. Just tell me when. I will be a little bit depressed, but inside. But tell me if you don't, because like if you hide it, it's even worse. Are you all happy with? So you are happy with what is the gradient descent so far? Miriam, you wanted to say something? I saw you activated your microphone.
Really? I didn't know. I didn't know.
The other Miriam, not you.
No, it's all right.
Sorry.
It's just like I moved to the quieter place, so I can activate it now.
Okay, so you are all happy with the gradient descent?
Yes.
Perfect. That's great.
Don't get depressed.
No, because we talked about it a lot of times, and we really like focused a lot on it. So that's great. So one of the problem of gradient descent, we update the weights by some value. This is the old value of a weight, and we update it by the gradient. This is the gradient, the slope, multiplied by a small number. It's a step. So we don't want a big step, so we don't have to jump. So this is the gradient, the value. So we multiply it by something, some small number, and we update my weight by this direction, for example. When it is negative, it goes to this direction. It becomes, here it's big, and then it becomes smaller. It becomes bigger, sorry, because this is negative gradient. So we keep updating it based on the magnitude of the slope. But if we pick this value, if we pick it too high, what will happen? Imagine we have this kind of, let's call it a plate-like shape. The minimum is here. So these are two features. This is my plate. The center of the plate is generally the minimum. or a bowl, or if you prefer, a bowl like that. This is my bowl. So the minimum is here. If we put a big step, we call this the step. So this is, we can go, the minimum should go towards this direction. But if here we use a too big of a step, we can end up here instead of going here. So we can go here. And if we use, again, bigger steps, we can, instead of going here, just here, we can go here. And we keep like oscillating and we keep just missing the minimum. We just keep spinning around. It's like someone who can't go straight directly to the point. He will just keep spinning around here. This is the effect if we choose a big step, or what we call the big learning rate. And if we use a smaller one, a very small one, what will happen? We might converge very slowly.
Slowly, yeah.
Yeah, if we take a small one, it will just take us days to converge and find like this minimum.
Each time we will make like very tiny
updates, yeah.
I call it, yeah, very tiny updates, yeah.
Yeah, and then it will take us a lot of time to reach the minimum. It's safer, but it can cost us a lot. So finding a good step or regularizing the gradient is very important. There are ways that are not used. I can mention one here. Don't worry if you don't get it fully, this method. There is what we call the Newton methods. Some of you guys who work in optimization, especially physics, etc., used to work with it. Newton methods, for example, when we have something like this, they compute the second derivative. The first derivative can give us the slope. The second derivative gives us if we are increasing in slope or decreasing. Here we are decreasing. So the next value is decreasing. Then decreasing, but here we are increasing. The gradient is increasing. So the second derivative tells us if the gradient is going up or is going down. If it is increasing, we can afford using big steps. For example, here, if it is the gradient is increasing, if we want to go up, we can afford to use big steps because the gradient is bigger. If we want to go up, normally we don't go up, but just suppose. If the gradient is decreasing, like in here, decreasing, we shall use smaller steps because we are close to the solution. So we don't jump. When we get close to the solution and the gradient is decreasing, we should use smaller steps. These are called Newton methods. It should use the second derivative. It tells us if the gradient is increasing or decreasing. The first derivative tells us what is the gradient, the slope, which is this angle basically. Second derivative tells us if it is increasing or decreasing, and even by how much, like the rate of increasing or decreasing. The problem with the second derivative is that it is computed by what we call the Hessian matrix, H, the Hessian matrix. If we have, for example, 1,000 variables or 1,000 parameters in my neural networks, so we need to compute the gradient for each one of them. Do you agree with me? We need to compute the gradient for each parameter and update them all based on their respective gradient. That is what we did. We generally do. Are you happy with this, guys? We compute the gradient in all. For example, here we have 2. We compute the gradient along this direction and this direction. We compute both gradients. Are you happy with this, guys?
Yes.
Yes.
The Hessian matrix. So how many gradients do we compute here?
2.
In this case, if we have 1,000. It's 1,000 gradients.
1,000.
Basically, for each variable, we need the gradient. For each variable, yeah, we need its gradient, and it is the derivative with respect to this gradient. The derivative of the loss function, of course. The Hessian matrix, which represents the second derivative, is a matrix. The size 1000 by 1000. It's a very big matrix to compute the second derivative. So each formula of each variable, each derivative with respect to one variable should be derived again with respect to all other variables. And same here, because we have 1000 functions. When we do the derivative, we get 1000 functions. The loss function will be derived with respect to all variables. So we end up with 1000 functions that are the derivatives of this. With the Hessian matrix, we derive all of these functions with respect to all the variables. So we end up with something like this. How many cells do we have here?
1000 times 1000?
Yeah, 1 million. So we used to compute here 1000 gradients, and here it's 1 million. And 1000 is a very small neural networks. 1000 is very small. Generally, a million is very common. A million by a million we will really struggle to just put it in memory. 10 power to 12. We will really struggle to put it in memory. So that's why we don't use Newton methods, the second derivative method. Although it can choose the optimal step because it knows by how much the gradient is changing. It is going to change by a big deal or by small deal, increasing, decreasing. So it can find the optimal step, but it's very, very expensive to compute. It is more expensive to compute than the actual gradients. So we don't use, this is just between parentheses, we don't use Newton methods. We use instead other estimations for this TK. So estimations that are less expensive. For example, so this is just an example for too small. We have multiple points. We are computing a lot of, we need a lot of iterations. If we use, for example, a very high learning rate here, the loss function will just go up because we are just jumping around. A low learning rate here, but it's slow to converge, as you can see, it's very slow. A high learning rate, as you can see, it's very fast in the beginning, but after that, it's not improving. It starts like oscillating or spinning around. A good learning rate can do this and get us to where we want. And this is not trivial to find. And as we said, with the second derivative, it's really good to find, but it costs us a lot. So what we do, one improvement is the momentum. The momentum moves faster with the direction of constant gradient. So if the gradient is constant, it is not changing a lot while we are moving, we keep a high step. But if it is not consistent, it changes all the time, like in here, it's changing all the time. The gradient is negative here, positive, negative, positive, which means that we need to go to oscillate a lot. We use a smaller step. We use here a smaller step, kind of step. So we move in a smaller way. So what happens? Instead of having this zigzagging like that, we will have something. We have less zigzagging, and we can converge faster, as you can see here. So if the gradient is not consistent, like it changes all the time in this direction, it is consistent. The gradient is almost the same. We need to move into this direction. But here we are zigzagging a lot on this dimension. We are always zigzagging. The gradient is positive, negative, because we are inside like a bowl-like shape. So it's always like changing the gradient, the sign of the gradient. So when we see that it is zigzagging a lot, we can just make its step or the update along this direction smaller. And here we can make it bigger because it's consistent. And we can end up with something like this. This is, of course, faster to convert than this. Okay, guys? This is the principle of momentum. Momentum is just like when you are in a slope like that, when you leave the ball, it will gain speed along if the slope is steep. And here the speed will be reduced a little bit. So here you build momentum, you keep building it, and once you reach here, it starts reducing a little bit in speed. If it is too flat, it starts reducing again. So this is what is meant by momentum. Okay, guys? Mathematically, it's not very complex. So here.
Sorry, Rida. So momentum, because it's a bit confusing. So momentum, it means we set up like small steps. Is it right?
Small steps, well, not small steps like let's call it small steps. Yeah, small steps when the gradient change too much, like in here, along this.
It's like the one that you showed us before, TK.
Yes, that one. Let's call it that way. It's not exactly here. The momentum. I will show you in the formula. It will be clearer.
Mm-hmm.
If the gradient changed a lot of change too much, like in here, it's positive, negative, like in a Bohr effect. So if we go here, the gradient change sign. If we go here, it change sign again. So it is changing the sign all the time because the update is in different directions. So here we probably will try a lower step. It's not really the step, but something very close. But along this direction, it is going forward. The gradient seems to not be changing too much. So we use a bigger one. Okay.
So we have two variables to set up. Like
yeah, we are in two dimensions.
And one is small and
here it's the variables are the number of weights here.
So in case, for example, as you said, we have 1,000 variable, so we have to set up like 1,000 steps.
Of course, yeah.
Ah, okay.
Or they will be updated differently.
Ah.
They will be updated differently. It's like, as I said, it's not exactly the step that we are changing.
Mm-hmm.
It's changing the gradient, but mathematically it will make sense. I will say.
The variation, are we changing like the variation or something like this?
How? Yeah, we are not changing. We're not updating the weights only based on the gradient, but we change the gradient a little bit. We take the cumulative gradient. Let's see the formula.
Okay.
This is the regular stochastic gradient descent. The next x, or the next value of the wave, equals the previous one minus the gradient multiplied by the step. This is the normal gradient descent. The gradient multiplied by a step size. With the momentum, instead of using the gradient, what do we use? We multiply it, we build the v, this v, which is, this is the gradient, the same gradient as in here, plus rho, this is a value, multiplied by the past v, the past v. It is like we are accumulating all the gradients, the past gradients, because this v is the past gradient plus the past v multiplied by something. It's almost like we are using the different gradients, fn plus here fn minus 1 multiplied by rho plus fn minus 2 multiplied by rho square. This is if we simply because this is like a series, vt plus 1, and here we have vt. So if you want to remove this v, this vt plus 1, here fn plus 1. This is rho, this is rho square, this is rho cube. It's something like this if we simplify it. We use the current gradient plus the past gradient multiplied by a constant that we choose, plus the gradient before it multiplied by the constant, this constant squared. Generally, this constant is a small number between 0 and 1. So just like we keep summing up all the gradients. We take into consideration all the gradients, but the latest one will be the one that is the most important. Then the one before it will be a little bit less important. And we keep going backward. This one is less important than this one, and we keep summing them up. It's like the sum of a series. So instead of using only here we are using only the current gradient. Here we are using the weighted sum of the past gradients, all the current gradient and the past gradients. So we're taking them all into consideration. Okay? So if this one is negative, and this one is positive, what will happen? This value will become smaller.
Yes.
Yes or no? It will become smaller.
Yeah.
So if the gradient change all the time, keep changing all the time, the total value will become smaller. And here, this value, we are not using the gradient, we are using this value v. It's like a speed or something, cumulative speed, will be smaller. If instead they are all positive, it means that we are all pointing towards the same direction. This v will become bigger. This one will become bigger. So it will reduce the zigzagging effect. If they change the direction all the time, along this direction will be a smaller value for the update. It will be something like this. And this one will become bigger along this direction because this sum, they are all positive or negative. And we will use a bigger value here. We don't really change the step. The step is in the next method. So we get something like this. And that way we converge faster. Faster than that way. Are you happy, guys, with this? It's a simple process. Happy? Happy or not?
To be honest, I didn't understand. Sorry.
No problem, no problem. Thank you for your courage. You're a brave one.
Maybe I'm slow to understand, but this one was like when you switch from the normal to the momentum, you are using the weight, correct? It's a bit confusing, yeah.
There is some weights, yeah. So I will draw it again. This one is simple so far. We are updating the gradient by the values by the gradient multiplied by the step. But here, what we are doing, we are not using the gradient to update the values. We are using this value, this v, which is this formula. This formula, just to simplify it, vt plus 1, to make it more simple, it is equal to what? This is the gradient, f, or delta, let's call it this gradient, plus the past gradient, this is fn, let's call it, the past gradient multiplied by rho plus n minus 2 multiplied by rho square till the end. Rho n minus 1 multiplied by f0, something like that. So this is equivalent to this because here we have vt. T is where we are. We call it n or t. So this is what is v equal to what? So it is equal to the current gradient plus the past gradient multiplied by rho. This is rho is always a number generally between 0 and 1. So it's a small number. So the path gradient will have a lower weight. The gradient before it will have even a lower weight, because this one, if it is 0.6, we multiply 0.6 by 0.6 and we get a lower weight. So we are summing them up, but the most important one will be which one?
Last one.
Last one. Exactly. What is happening here? Here we replace this, the regular gradient, with this value instead, with this. We replace this, that was in here, by this. In case the gradient is changing all the time, positive, negative, positive, negative, what will happen? For example, if this is positive and this is negative, what will happen? The value will become smaller.
Correct.
If they are both positive, the value will become bigger. So if the gradients and the path gradients are consistent, it means they don't change sign over time. This value will become what?
Bigger.
Exactly, it will become bigger. Oh, and if it is the opposite, if they
It becomes
have
smaller.
it becomes smaller. Exactly. So we are multiplying the step. If there is consistency, we multiply it by a bigger value. If there is no consistency between them, we are multiplying the step by small value. And this will transform this zigzagging into something like this.
Reda, what would decide the consistency of the gradient?
This one. This one.
Okay.
A consistent gradient will be always positive. But it's itself and the past gradients. For example, this one, when we move here along this direction, the gradient is positive, 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 positive. The gradient is always positive. But here, the gradient is changing its sign all the time. Negative, positive, negative, positive, negative. It's always changing. Along this value, it's always going up and down. But here, it's always going up, going towards this direction, which means the gradient is always pointing towards this direction along this side. But here, it's always pointing to sometimes positive, negative, positive, negative. So here it is inconsistent. That's why this V value will be small. But here it is consistent. This V value, if we sum up the gradients all of them with the weights, we sum them up,
would be big.
Make this one bigger. So this is the effect of this formula on the gradient. So if it is consistent, it just means we build momentum. The gradient is always positive. We keep it's like rolling here. But if it is not consistent, like in here, in the ball inside, if we keep going to both directions, it's not consistent. We are just like balancing, or so it means that this value will become smaller. So if it becomes smaller, instead of zigzagging that way, we will zigzag in a less. We can have something like this. And this doing things this way is faster than doing things this way. Okay, because here we are using lower step than here and here, and here a higher, not step, but this value. Is it clear, guys?
Yes.
It should be
Yes.
okay. It should be at least okay-ish.
Yeah, it's okay.
So now this is for the gradient and the momentum. Now another very successful method that is a little bit different than the momentum. It is called RMS prop. What is funny about this method is that it has never been published in a research paper or so. It was just an idea, but by Jeffrey Hinton, which is one of the superstars of machine learning around the world. He just developed it during a course he was giving, one of his courses. During a lecture, he thought about the method and developed it, and then it was used like now by almost every library, every machine learning library. It's called RMS prop. RMS prop, the momentum change just like later use the cumulative gradient. RMS prop instead changes the step. So this is the gradient. So this is the formula, x. We update it by the past value of x, the other weight, multiplied by the gradient. This is the regular gradient descent. Here we multiply it by a step. The RMS prop tries to change the step for all parameters. It doesn't use the same step. So this is the step that we choose in the beginning, and we divide it by this value. What is this S? This is just a small number to avoid the division by 0. So what is this S? S is what? Is the past S multiplied by a value. This is also a small number. This gamma, or this is a small number between 0 and 1. But here we multiply it. So if it is equal to 0.5, this value will be also 0.5, something like that. Generally, we use 0.9 here, and here 0.1. We multiply it by the square of the gradient. By the square of the, what does it mean? If the gradient is too big, we will use a smaller step, because if the gradient is too big, the current gradient and the past gradient as well, it is also equal to the sum of the gradients, of the square of the gradients, weighted. If this one is too big, what will happen to the step? If the S is too big,
It will be small.
Exactly, it will be small. If this is very small, for example, less than 1,
big.
It will be bigger. So when the gradient is too big, we use smaller steps. It means if the gradient is too small, you can afford bigger steps, because the change will be very small, because this value is going to be small. So we can afford bigger steps, and vice versa. It can also help to reduce zigzagging as well, because when we have this zigzagging, the gradient tends to be too big, a lot big, when we have zigzagging, like the ball effect that we saw. Like the surface of a ball is it has a high gradient. So that way we use a lower step, so we can, instead of jumping here, we go here, and it will reduce zigzagging. So if the gradient is too small as well, we can afford bigger steps. So this is how RMS prop works. We have another method. I didn't use the formula here, but the formula is very simple. It's just, this method is one of the most used. It's like the star method for gradient descent. It's called ADAM. One of the most successful methods, algorithms. It's a bit like a combination of RMS prop and momentum. You can Google it. It's, when you look at the formula, it really looks like we actually use the S, and we use as well the V. And we change this by what we had in the momentum, and here we keep this, what we got from RMS prop. This is basically the formula for ADAM. And default parameters, by default, that the researchers found, and they are surprisingly good. We don't need to change them a lot to get decent results. This is for ADAM, which is a combination of RMS prop, which is changing the step size dependent on the momentum, on the gradient and past gradients, and the momentum, which also like change the gradient value depending on the past gradients. And the combination of these two really gives something super strong, which is ADAM. Okay, guys, happy so far? And it really depends on your case. Sometimes using ADAM is better. Sometimes using just RMS prop is better. Sometimes using momentum is better.
So we have to test them to know, or
Yeah, kind of. You will learn when you can. Well, there are some parameters that works most of the time. You can. It's a trial and error also thing. You try one and you see if it works or if it converges or not, and you keep changing them until you get good results. And also, you can change these values. This one, these are parameters. This value and this value. These are two parameters, for example, for RMS prop. For momentum, also we have this row as a value, as a parameter. And alpha also, the step is also a parameter. So sometimes you need to change them, but with these methods, you don't need to do a lot of work around them. You try a few of them and see. ADAM works very well. RMS prop for me worked really well. So we are done with this chapter. There are a lot of things we can see. It's not the only thing, but these are like the most important aspects of what I wanted to show you guys. I think I should give you a pause now. Let's have a pause.
This conference will now be recorded.
So CNNs, convolutional neural networks. Before, let's have a look at what images are. Generally, it's just a matrix or a tensor. For example, this image is simply a matrix of 64 by 64, which is the size of the image. Each cell of the matrix represents 1 pixel. Very simple representation. Or we can have a single channel, like in here. Or we can use 3 channels. 3 channels, it means something like RGB. Each color, each pixel has 3 components, red, green, and blue, which represent what?
The main colors.
Exactly, the color. So, for example, if this is blue, we will have a lot of blue here, possibly 200. Then green, I don't know, maybe 50. And red, maybe 80. So this, possibly, I'm not sure, we can find out. Possibly this blue is encoded into these values. 200 blue, 50 green, 280 red. The maximum number is 255 generally. So this is encoded into a tensor. So a matrix with one value is a matrix. A tensor is 3D. So we have 3 values. So each pixel has 3 values, R, G, B. So this is a tensor. This is how generally an image is represented. A grayscale image requires only 1 value. A color image requires three channels generally. A grayscale image will require only 1 value, which will make it a matrix. A matrix like this. We don't need RGB, we need only 1 value per cell, not 3 values like in here. So pixels, they represent colors. Grayscale requires only 1 channel. RGB is typically used in deep learning, which means 3 channels. There are others like lab, HSV, which are different than RGB. 3 channels as well for lab, for HSV, and there are also others to how to represent colors. But RGB is the most common one. Red, green, blue. Okay, guys. How would you build a model using neural networks to recognize these images of cats? If there is a cat or not. How many input will we have here? How many input?
3.
No, for this image. 3? For this image, just 3? We have a whole image.
64 times 64.
Yeah, so each pixel will be an input. Exactly, 64 by 64 by 3. Thank you, Abbas. 64 by 64 by 3, which means over 12,000 inputs. And this is a very small image. 64 by 64 is super small. It's like an icon. So if the first hidden layer, we have here 1,000 neurons. 1,000 neurons. And here we have how many? We have 12,288 inputs. So how many weights we will have here? We have here 1,000 neurons, 12,288 inputs. How many weights, total weights, we will have only in this layer? Total weights. How many?
1,000.
12.
How many? Sorry?
Is it 1,000?
We have 1,000 neurons. Each neuron has a number of weights. This is how neural networks work.
12 billion.
12.
Yeah.
12 million.
12.
Multiplied by, yeah.
Exactly. 12 million. Thank you, guys. 12 million weights just for this kind of images to recognize them. It's a bit insane. 12 million, and this is just for this layer. This layer is smaller because we have just one input here, one output that is given here. So here we have 1,000. If we have here 1,000, we will have here 1 million. It's smaller. So here we will have 12 million. Here we will have 1 million parameters inside. This is quite big and very hard to train. And imagine if we had a regular image of 500 by 500, what will happen? It's multiplied by 3, which means 7 million. And half pixels or per tensor. This is its size. If we use 1,000, 1,000 is nothing as a number of neurons compared to the number of inputs. Generally, it scales with the number of inputs. If we use only 1,000, it will become 7 billion for an image of 500 by 500, which is the typical size, normal size for images, even not that big. It will be 7 billion parameters only here. A lot. Again, if we train a neural network that can recognize the first image as a flower, will it be able to recognize the second image as a flower? What do you think?
Yes,
Why?
because like it's under that square, so it's the same.
It will recognize it because every pixel will be a feature. If it wasn't trained to recognize images into this zone, because this zone represents inputs for different inputs than this one. This zone represents different inputs. So for the first zone here, it will be some inputs at the top, but this zone will be some inputs at the bottom.
Yes.
So if we never had an image here, a flower here, the network will struggle with it. If we never in the data set we never had a flower here, the network will have a problem to recognize that we have a flower because it learned only flowers in this region, and these features were never had any flower. So it will probably struggle with it if the data set didn't have flowers in this place. Normally we need a neural network that is location invariant. It shouldn't care about where the flower is. It should recognize it no matter where it is. We need something like that.
Yes.
Okay. Now let's have a look at the visual cortex, how it works in our eyes and the frontal lobe of our brain. So in the visual cortex, nearby cells represent nearby regions in the visual field. So we have cells that are connected like next to each other, and each cell is responsible for a certain field in the space that we are seeing, and nearby cells are responsible for close regions, very close regions. This cell and this cell are responsible for close region in the space we are looking at. So neurons close to each other are responsible for things that are close in terms of spatial representation. This is how our brain works. For example, and it is also hierarchically organized. Neurons are stacked in layers. Let's see what this means. First layer neurons will recognize simple shapes. So we have the neurons that are connected to a small region, and they are recognized to simple. They can recognize simple shapes. And then we have other neurons after them, another layer, that are connected to this first level neurons. And this other layer is capable of combining what the first neurons has recognized. For example, this is an image. This is a neuron that is focusing only on here. This neuron is in here. This one is in here. So each neuron is focused only on a portion of the image, not all of the image, like in the regular neural networks. Each neuron will be focusing on the entire image. All the input will go in. So if this neuron is able to recognize this one, this kind of shape, and this one is able to recognize this kind of shape, this one, this shape, and this one, this shape. And then we have another neuron that is using the information provided by each one of them. So this neuron will say yes or no if this thing look like this shape. It says yes or no if this thing looks like this shape. Same for here and same for here. So this one will recognize what?
The whole circle, I mean the whole image.
And what is it?
The first circle. The square.
Exactly. Abbas said, yeah, Usama said the combination, yeah. But not what do we have in the square?
The image.
We'll have
the
a rectangle.
Flower. Okay.
Because this one recognizes this type of edge here. This one recognizes this type of edge. This one, this type of edge. And this one, this type of edge. They are connected spatially. They are connected next to each other. So this one is able to recognize squares or rectangles or whatever we can call them. Because the first layer is able to recognize simple shapes. This one also has its sister neurons, if we can call them that way, and they will do the same thing. They recognize something. Same goes for other neurons here. Maybe a neuron here will recognize triangles, a neuron here will recognize circles, etc. And then we have another level of neurons here that takes again these shapes. Combine them, for example, to recognize something like this. Sorry for the drawing. It is possible. So each of this neuron is specialized in recognizing a more complex shape: triangle, circle, rectangle, etc. And then another neuron here takes everything and is able to recognize something more complex. And it doesn't care where it is. We can move around, like take this neuron and make them focus elsewhere. This thing will always be able to recognize this guy if we put them to focus elsewhere, because this one is specialized in this type of edges. This one is specialized in combining these edges. Same for the triangle, same for the circle, etc. If we make this receptive field for either all of these neurons move away, we can always still recognize this guy, because they know what is a rectangle. They don't recognize everything in the image, They know how to know where is the rectangle, where is the circle, where is the triangle, and another neuron knows how to combine them to recognize this, guys. So this is the motivation behind convolutional neural network. A neuron is connected only to a small number of inputs instead of the whole image, like in regular neural networks. A small number of inputs, just a small region. And we have other neurons that are also connected to a small region. And these neurons are also neighbors. We know they are next to each other in the image. And then we combine them to make bigger shapes. So the first layers of the neuron will recognize like edges, horizontal line, vertical line, things like that. The other layer will recognize things that are more complex. The following layer will do the same thing, and we build in complexity until we recognize a face, an entire face. This is the principle. Okay, guys, any questions so far? Any question?
Please,
it's clear for me.
Yeah.
Just to clarify, what about the positions? I mean, you were talking about the shapes.
Yeah,
and,
the positions. Yes, the positions. This is a simple, very simple example. I will show you about the position. This neuron, normally, it will be connected to all the images at different, in the beginning, it will be connected only to this region. Then we convolve. I'm going to show you this example. It move a little bit and see if this edge exists here. It recognizes this edge. It is connected here in the beginning. It looks if there is this edge there. Then it moves a little bit and try to recognize it if it is in here and try to get where this edge is. It scans the whole image, but just a small portion at a time. So it is like position invariant. It looks at it convolves. I'm going to show you like better examples of this convolution. We call this convolution. Are you happy with this explanation?
Yes, okay. Thank you, Reda.
Thank you, Osama. We are going to look at it deeply. So this is, do you understand what we are doing here? It's like we have stages of neurons that are specialized in simple shapes, then neurons that are specialized in slightly more complex shapes, and so on, until we get a very high complexity. This is the principle of convolutions. This neuron also will be connected only to a small portion, not to all the neurons like in regular neural networks. Same here, it is connected only to a small portion of the input. Same here, it is also connected to a small number of neurons. Okay, guys? So the difference between them is that we are reducing the number of weights. Okay, guys? We are reducing the number of weights by a lot, because if this one is connected only to 4, all the other connections are reduced. So the number of parameters will be a lot smaller. Do you agree with me? The number of parameters is going to be smaller. Are you happy so far?
Yes, yeah.
Perfect.
Does that mean that we are improving the learning process? Is that
the speed? The speed, and not just first the speed. It's clear that the speed is better, but also convergence. We will learn in a much faster way, and we are going to see why.
okay?
So this is one example of CNNs. So here, the first neurons are learning like this kind of edges. Second neuron are combining them to learn nose, eyes, etc. And third level of neurons, we call them actually filters, are learning faces because they can combine eyes and they learn different types of faces. They can recognize faces. Okay, guys, this is the principle of convolutional neural networks. This is one of the first architectures of ConvNet, LeNet. It was used to improve document recognition. characters level. So we have inputs, and then we try to recognize the shape here and combining them. Like the first layer will recognize small shapes. The next one will combine them until we can recognize what letter it is. This I'm hoping that we can do this example or something close to this example next time. Now let's look at the convolution layer. This is one neuron that is, say, it is specialized in recognizing this edge. So because we want the neuron to be location invariant, we want the neuron to tell us where is the edge. So what we do, we slide it. This neuron is connected in the beginning only to this small portion, but we slide it along the image. And it will tell us where is this edge. Do we have this edge here? Do we have it here? Do we have it here? So what we are doing is something like here. We slide it. When we slide it, a normal neuron, guys, how many outputs does it have? How many outputs for a single neuron? Normally?
One.
Only one, exactly. A neuron is like this, multiple inputs and one single output. It can go to multiple neurons, that is fine, but it is one single output. But here, because we are convolving, how many outputs we are going to have?
Depending on the edge?
Depending on the size, actually, of the image.
Okay.
It will tell us, the neurons will give us also another feature map that tells us if this edge is present or not. Let's make it simple. That's the Boolean number. 1 when it is present, 0 when it is not. So it gives us what we call a feature map. 0 and 1, for example, it is different, not like that generally, but something like that. That is 0 and 1. It tells us, so this kind of neuron, instead of giving us only one output, is going to give us multiple outputs. But it can recognize only one type of edge. Only, for example, this edge. Okay? But we will have multiple outputs because we are convolving. We are not taking the whole image. We are rather taking a small portion at a time and moving, like sliding. We call this convolve. Sliding along the image, rows and columns. And we get where is the shape. So yeah, this is the image, 32 by 32 by 3, number of channels. Well, we call this a 5 by 5 by 3 filter. 5 by 5 is the size, and 3 is the number of channels. So we take 3 channels and 5 by 5. When we do that, and we slide along the image, we get something like that, 28 by 28 by 1. And in each cell, it tells us if we have the shape that we are looking for or not, the shape or whatever. So we get something like that. This neuron can recognize how many types of shapes?
Only one.
Oh, perfect, only one. It cannot recognize more than one. Then, to recognize more, we add another neuron. We had the blue neuron. And then now, to recognize more shapes, another shape, we use another neuron. For example, this one is able to recognize this shape. We do the same thing again with it, and we get another feature map. So the feature map is, let's say, this shape. The second feature map is this shape. So we know when we have this, by 0 and 1, for example. Same here, 0, 1. We know when we have this and when we have this. So when we have, for example, here this is it means that we have this shape, and here we have, say, 1. It means that we have this shape here. Here we have in this cell we have this shape, and in this cell we have this shape. It means that the image is something like that. We are close to the rectangle. So here we have two activation maps, two maps. One that tells us where is the shape, and the other one will tell us where is this second shape. And we can have how many a lot more. You can have a lot more. Each one is specialized in what?
In one field.
Specific.
Perfectly. So here we have 6. So we are recognizing 6 types of shapes. Perfect. Generally, after each convolution layer, a convolution layer is just one neuron is doing. One single or multiple neurons, sorry. Multiple neurons are doing. So this is a convolution layer. It takes it uses few neurons and get me this activation map. Generally, we add an activation function like the sigmoid that we talked about last time. But here we use the rule. We are going to see why instead of the sigmoid. Sigmoid is just to convert it between 0 and 1 to say yes or no. We get a number and we convert it into 0 or 1. Yes, no. But instead of that, we use the sigmoid, and it is we use the Rulu, and it is a lot more efficient than the sigmoid in the case of CNNs. And then what happens? We stack, so we have the image and the convolution layers, plus the Rulu that transform the values into yes or no, kind of yes or no, the activation function. We get a feature map. We do the same thing again, convolution layer, Rulu. Here we have simple shapes. Here we have other neurons that will recognize more complex shapes. And we add convolution and Rulu to tell us if it is this circle and squares. And we keep going on. We keep putting convolution layer, Rulu, convolution layer, Rulu, etc. until we are able to recognize very complex features. Here, generally, the more in depth we go, the more filters we have. Because, guys, the number of simple shapes is limited. Like this. Generally, it is limited, 6. The more complex we go, the more like variants we have. For example, when we combine them, like getting circle, square, star, we have more possibilities when we go in complexity. So generally, we go higher by a high number of filters or neurons, how many types of shapes we can learn. And if we go here, we might go with like 20. So the higher we go in complexity, the more choices we have. Because simple shapes we don't have a lot, but the way on how to combine them, we will have more, and so on. Happy with this, guys?
Yes.
Perfect. Now we will finish with this probably. I think it's too much here. Let's have a closer look with the convolution. So one neuron is connected to this 3 by 3. And then when we slide, we don't jump generally here. We jump by just 1 because we are looking at just to the nearby. If this shape doesn't exist here, for example, it doesn't exist here, it is in here. We are not able to recognize it here. But if we move by 1, we can recognize it. So we call this stride equal 1, 3 by 3 filter, a 3 by 3 filter, because of the size of how many inputs are connected to my neuron. And the stride 1, it means we are moving just by one cell into when we convolve. And same goes into this direction as well. So here we get 5 by 5 outputs. 5 by 5, because here it's 1, 2, 3, 4, and when we move to the last one, it's 5. This is the process of convolving. Now, stride equal 2. With stride equal 2, we jump by 2, like in here. So we get 3 by 3. The higher the stride, the smaller the image, the feature map will be. Here, it's going to be 3 by 3. So here, the first one, second one, third one. So we end up with something like a filter of 3 by 3. And now strike equal 3. So we jump entirely. We go here. Sorry, normally I should have drawn it here. So we will have a problem. We cannot. We will have this left, this part left. In these cases, generally what we do, we add what we call padding. We add zeros around, so we don't have this problem. When we add zeros, we will have like enough space to build like 3, 3, and 3. So we'll have 3 by 3. In these cases, we use padding. Let's stop here, guys. I think if you want to continue, we can continue, but I think it's we covered many things today.
Yes.
You're tired. So yeah, let's continue next time with convolutional neural networks. And let's stop for now.